Abu Hanifa al-Dinuari. d. 895 CE. Abu Hanifa al-Dinuari, d. 895 AD, lived in Andalusia, Muslim Spain. His work has been made known by the German scholar Silberberg in a thesis in Breslau in 1908, which contains the descriptions of about 400 plants. However, what is described by Silberberg is just a little part of what has survived, just 2 volumes out of the 6. In his exposé on the Earth, al-Dinuari describes a variety of soils, explaining which is good for planting, its properties and qualities. Al-Dinuari also describes plant evolution from its birth to its death, including the phases of growth and production of flower and fruit. He then covers various crops including cereals, vineyards and date palms. Relying on his predecessors, he also explains trees, mountains, plains, deserts, aromatic plants, woods, plants used in dyes, honey, bees, etc. Al-Dinuari also devoted 1 chapter to the classification of plants, Tajniz al-Nabat, which he mentions in one of the volumes that have survived, but the work itself on the subject has also been lost. Al-Dinuari's Book of Plants also covers various other subjects such as astronomy and meteorology. Thabit ibn Qurra, 836 to 901 CE. Thabit ibn Qurra ibn Marwan al-Sabi al-Harani was born in the year 836 CE at Harran, present Turkey. As the name indicates, he was basically a member of the Sabi sect, but the great Muslim mathematician Muhammad ibn Musa ibn Shakir, impressed by his knowledge of languages, and realizing his potential for a scientific career, selected him to join the scientific group at Baghdad that was being patronized by the Abbasid caliphs. There, he studied under the famous Banu Musa brothers. It was in this setting that Thabit contributed to several branches of science, notably mathematics, astronomy and mechanics, in addition to translating a large number of works from Greek to Arabic. Later, he was patronized by the Abbasid Caliph al-Mu'tadid. After a long career of scholarship, Thabit died at Baghdad in 901 CE. Thabit's major contribution lies in mathematics and astronomy. He was instrumental in extending the concept of traditional geometry to geometrical algebra and proposed several theories that led to the development of non-Euclidean geometry, spherical trigonometry, integral calculus and real numbers. He criticized a number of theorems of Euclid's elements and proposed important improvements. He applied arithmetical terminology to geometrical quantities, and studied several aspects of conic sections, notably those of parabola and ellipse. A number of his computations aimed at determining the surfaces and volumes of different types of bodies and constitute, in fact, the processes of integral calculus, as developed later. Thabit ibn Qurra was a native of Harran and a member of the Sabian sect. The Sabian religious sect were star worshippers from Harran, often confused with the Mandaeans, as they are in 1. Of course, being worshippers of the stars meant that there was strong motivation for the study of astronomy, and the sect produced many quality astronomers and mathematicians. The sect, with strong Greek connections, had in earlier times adopted Greek culture, and it was common for members to speak Greek, although after the conquest of the Sabians by Islam, they became Arabic speakers. There was another language spoken in southeastern Turkey, namely Syriac, which was based on the East Aramaic dialect of Edessa. This language was Thabit ibn Qurra's native language, but he was fluent in both Greek and Arabic. Some accounts say that Thabit was a money changer as a young man. This is quite possible, but some historians do not agree. Certainly he inherited a large family fortune and must have come from a family of high standing in the community. Muhammad ibn Musa ibn Shakir, who visited Haran, was impressed at Thabit's knowledge of languages and, realizing the young man's potential, persuaded him to go to Baghdad and take lessons in mathematics from him and his brothers, the Banu Musa. In Baghdad, Thabit received mathematical training and also training in medicine, which was common for scholars of that time. He returned to Haran, but his liberal philosophies led to a religious court appearance when he had to recant his heresies. To escape further persecution, he left Haran and was appointed court astronomer in Baghdad. There Thabit's patron was the Caliph, al-Mu'tadid, one of the greatest of the Abbasid caliphs. At this time there were many patrons who employed talented scientists to translate Greek text into Arabic, and Thabit, with his great skills in languages as well as great mathematical skills, translated and revised many of the important Greek works. The two earliest translations of Euclid's Elements were made by al-Hajjaj. These are lost except for some fragments. There are, however, numerous manuscript versions of the third translation into Arabic, which was made by Hunayn ibn Ishaq and revised by Thabit. Knowledge today of the complex story of the Arabic translations of Euclid's Elements indicates that all later Arabic versions develop from this revision by Thabit. In fact, many Greek texts survive today only because of this industry in bringing Greek learning to the Arab world. However, we must not think that the mathematicians such as Thabit were mere preservers of Greek knowledge. Far from it, Thabit was a brilliant scholar who made many important mathematical discoveries. Although Thabit contributed to a number of areas, the most important of his work was in mathematics, where he played an important role in preparing the way for such important mathematical discoveries as the extension of the concept of number to positive, real numbers, integral calculus, theorems in spherical trigonometry, analytic geometry, and non-Euclidean geometry. In astronomy, Thabit was one of the first reformers of the Ptolemaic system, and in mechanics he was a founder of statics. We shall examine in more detail Thabit's work in these areas, in particular his work in number theory on amicable numbers. Suppose that, in modern notation, Sn denotes the sum of the aliquot parts of n, that is the sum of its proper quotients. Perfect numbers are those numbers n with s, n, equals n, while m and n are amicable if s, n, equals m, and s, m, equals n. In book on the determination of amicable numbers, Thabit claims that Pythagoras began the study of perfect and amicable numbers. This claim, probably first made by Iamblichus in his biography of Pythagoras written in the 3rd century AD, where he gave the amicable numbers 220 and 284, is almost certainly false. However, Thabit then states quite correctly that although Euclid and Nicomachus studied perfect numbers, and Euclid gave a rule for determining them, 6, or 7, neither of these authors either mentioned or showed interest in amicable numbers. Thabit continues, 6, or 7. Since the matter of amicable numbers has occurred to my mind, and since I have derived a proof for them, I did not wish to write the rule without proving it perfectly, because they have been neglected by Euclid and Nicomachus. I shall therefore prove it after introducing the necessary lemmas. After giving 9 lemmas, Thabit states and proves his theorem, for n greater than 1, Let Pn equals 3.2n minus 1 and Qn equals 9.22n minus 1 minus 1. If Pn1, Pn, and Qn are prime numbers, then A equals 2n Pn1 Pn and B equals 2n Qn are amicable numbers while A is abundant and B is deficient. Note that an abundant number n satisfies S, n, greater than n, and a deficient S, n, less than n. More details are given in 9, where the authors conjecture how Thabit might have discovered the rule. In 13, Hagendijk shows that Thabit was probably the first to discover the pair of amicable numbers 17,296, 18,416. Another important aspect of Thabit's work was his book on the composition of ratios. In this, Thabit deals with arithmetical operations applied to ratios of geometrical quantities. The Greeks had dealt with geometric quantities but had not thought of them in the same way as numbers to which the usual rules of arithmetic could be applied. The authors of 22 and 23 stress that by introducing arithmetical operations on quantities previously regarded as geometric and non-numerical, Thabit started a trend which led eventually to the generalization of the number concept. Thabit generalized Pythagoras's theorem to an arbitrary triangle, as did Pappus. He also discussed parabolas, angle trisection and magic squares. Thabit's work on parabolas and parabolids is of particular importance since it is one of the steps taken towards the discovery of the integral calculus. An important consideration here is whether Thabit was familiar with the methods of Archimedes. Most authors, see for example, 29, believe that although Thabit was familiar with Archimedes' results on the quadrature of the parabola, he did not have either of Archimedes' two treatises on the topic. In fact, Thabit effectively computed the integral of x and 1. The computation is based essentially on the application of upper and lower integral sums, and the proof is done by the method of exhaustion. There, for the first time, the segment of integration is divided into unequal parts. Thabit also wrote on astronomy, writing concerning the motion of the eighth sphere. He believed, wrongly, that the motion of the equinoxes oscillates. He also published observations of the sun. In fact, 8 complete treatises by Thabit on astronomy have survived, and the article 20 describes these. The author of 20 writes, "When we consider this body of work in the context of the beginnings of the scientific movement in 9th century Baghdad, we see that Thabit played a very important role in the establishment of astronomy as an exact science method, topics and program which developed along 3 lines: the theorization of the relation between observation and theory, the mathematization of astronomy, and the focus on the conflicting relationship between mathematical astronomy and physical astronomy." An important work, Kitab fil Karastan, the book on the beam balance, by Thabit, is on mechanics. It was translated into Latin by Gerard of Cremona and became a popular work on mechanics. In this work, Thabit proves the principle of equilibrium of levers. He demonstrates that 2 equal loads, balancing a third, can be replaced by their sum placed at a point halfway between the 2 without destroying the equilibrium. After giving a generalization, Thabit then considers the case of equally distributed continuous loads and finds the conditions for the equilibrium of a heavy beam. Of course, Archimedes considered a theory of centers of gravity, but in 14, the author argues that Thabit's work is not based on Archimedes' theory. Finally, we should comment on Thabit's work on philosophy and other topics. Thabit had a student Abu Musa Isa ibn Usaid who was a Christian from Iraq. Ibn Usaid asked various questions of his teacher Thabit, and a manuscript exists of the answers given by Thabit, this manuscript being discussed in 21. Thabit's concept of number follows that of Plato, and he argues that numbers exist, whether someone knows them or not, and they are separate from numerable things. In other respects, Thabit is critical of the ideas of Plato and Aristotle, particularly regarding motion. It would seem that here his ideas are based on an acceptance of using arguments concerning motion in his geometrical arguments. Thabit also wrote on 1. Logic, psychology, ethics, the classification of sciences, the grammar of the Syriac language, politics, the symbolism of Plato's Republic, religion and the customs of the Sabians. His son, Sinan ibn Thabit, and his grandson Ibrahim ibn Sinan ibn Thabit, both were eminent scholars who contributed to the development of mathematics. Neither, however, reached the mathematical heights of Thabit. Reference